We'll practice using the photoelectric effect to find the kinetic energy and speed of ejected electrons. Here's the problem. Light of wavelength 400 nanometers strikes a metal whose work function is 2.0 electron volts. Given Planck's constant, speed of light, electron mass, and the conversion factor for electron volts to joules, find the maximum kinetic energy of the ejected electrons and the maximum speed. First, find the photon energy using the formula E equals hc over lambda. Plugging in the numbers, we get 4.97 times 10 to the minus 19 joules. Convert to electron volts by dividing by 1.6 times 10 to the minus 19, giving 3.11 electron volts. Now apply the photoelectric equation. Maximum kinetic energy equals photon energy minus work function. Subtracting gives 1.11 electron volts. Convert to joules by multiplying by 1.6 times 10 to the minus 19, given 1.78 times 10 to the minus 19 joules. For maximum speed, use kinetic energy equals 1/2 mv squared and solve for v. V equals the square root of 2 times kinetic energy divided by mass. Plugging in the numbers gives the square root of 3.9, 1 times 10 to the 11, which is 6.3 times 10 to the 5 meters per second. Remember, the photoelectric effect shows that the maximum kinetic energy of ejected electrons is the photon energy minus the work function, and you can find their speed from that energy.